This is a walkthrough of problem 3 on practice exam 4 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. This is the tidal volume versus time for a ventilator for infants. Improper ventilation can cause lung injury, the most common of which is bronchopulmonary dysplasia, which is basically lung damage. So this is the volume versus time. So you can imagine this is like a balloon that you're blowing up and letting the air out, and this is the profile of the volume of the balloon. So let's take these one at a time, starting with what is the average airflow rate into the lungs over the time interval from 0 to 2 seconds. Average flow rate. You have to think about this. Try to understand what this is asking. The average flow rate. Can you think about how to get this? If you haven't thought about it for a long time, you probably should think about it now. What does this graph mean? Look at the units, volume versus time. Try to wrap your head around it instead of trying to figure out what I'm supposed to do. Imagine this. So the total volume went from 0 to maybe 24 cc's in 2 seconds. The average flow rate, 24 cc's in 2 seconds, 12 cc's per second, right? Makes sense. B, what is the average flow rate into the lungs over the time interval from 2 to 2.01 seconds? Man, what's the average flow rate there? The average flow rate doesn't change that much. The flow rate doesn't change that much, not the average flow. The flow rate doesn't change that much from 2 to 2.00. It changes a lot from here, from 0 to 2. It doesn't change much from there. So I think we can just get the slope. The slope is the flow rate. The average flow rate from 2 to 2.001 is the same. Virtually the same. So we're going to locate the point, draw a good tangent line. Goes from 16 to 30. That rise is 14 cc's. The run looks like about 3.5 seconds, right? 14 cc's in 3.5 seconds. That's the flow rate at the point, 2 seconds. Or you can say it's at the point at 2.00. The flow rate at 2.001 seconds, you can't tell the difference. 4 cc's per second. And since that's the flow rate at 2 or around 2, that's the average flow rate from 2 to 2.001. It's got to be 4 cc's per second. Can't change much over a thousandth of a second. Right? If the question asks for the tangent line at 2.001 seconds, it's the same line. We wouldn't draw a different line. We couldn't possibly draw a different line. So on to part C. What is the average flow rate into the lungs over the time interval from 2 seconds to 2 seconds plus dt? I love this problem because it tests your understanding of infinitesimals. It's 4. It's got to be 4 cc's per second. Part D. What's a good estimate of dv dt at t equals 0? dv dt is the slope, dv is the rise, dt is the run. I want to know the initial. That's pretty steep. So we draw a tangent line at t equals 0. The rise is 30 cc's, obviously. And the run looks like a little bit bigger than 1.5 seconds, 1.6 seconds. Slope is 30 cc's in 1.6 seconds, so 18.8 roughly. We can call it 19 if you want, cc's per second. That's the initial flow rate, the flow rate at time equals 0. Part E, what's a good estimate of dv dt at 2 seconds? We're just testing you here. You've been paying attention? It's 4 cc's per second. The average flow rate from 2 seconds to 2 seconds plus dt is the same as the flow rate at 2 seconds. What is the infinitesimal volume dV that flowed into the lungs in the time interval from t equals 2 seconds to t equals 2 seconds plus dt. the air that flowed into the lungs in the time interval 2 seconds to 2 seconds plus dt. We know what the flow rate is at 2 seconds. dV dt is 4 cc's per second. And that's dV dt, and we want dV in terms of dt. So we multiply both sides by dt, and that's the answer. This is some really nice calculus concepts, developing a fundamental understanding of the infinitesimal. Make sense? That's the key. After a while, you do a few hundred of these and you say, I think I understand what's going on here. This makes sense to me.